Welcome back. It's time to put all of these things that we've developed together to do something really cool. But before we do that, let's quickly recap where we're at. Let's take a moment and have a mole appreciation minute, if you like. So we're taking a very new look at the world. We've realized that when we want to build molecules, when we want to build compounds, we need to do it atom by atom, but they're just too small for us to count out. So we've developed this whole new way of counting, the mole concept. The idea that we can count things not by the atom, but by Avogadro's number of them, by 6.022 times 10 to the 23 of them. We've then looked at how we can relate this number of moles to masses, concentration, volumes, all kinds of everyday things. So I've been building these skills for you, obviously for a reason. And that reason is happening now in this very topic. To discuss this further, let's go back to our old friend here. Let's go back to the rusty car. So you can see here I've got my car once again. It's rusting. And we've had a look at this chemical equation before. And we looked at it, it says 4 iron plus 3 oxygen gives 2 iron oxide. We talked about those coefficients and we said, yep, that tells us how this reaction occurs. It says that 4 atoms join together with 3 molecules of oxygen to make 2 iron oxides. That's what takes place. It doesn't have anything to do with mass though. It doesn't have anything to do with grams. It's not 4 grams, 3 grams, 2 grams, nothing like that. But I think you'll now appreciate where this is going. What we can say is we can scale up from those impractical little atoms and molecules. We can say that this reaction involves 4 moles of iron reacting with 3 moles of oxygen to make 2 moles of iron oxide. So we're scaling everything up to a much more manageable size. What this then effectively means, if you have a look at this chemical reaction, if I have 4 moles of iron, I know that it will eventually rust. And this reaction tells me that when it rusts, when it breaks down, I will end up with 2 moles of iron oxide. Look at it differently. If you come across a pile of iron oxide and think, my iron's rusted. If you know how many moles of iron oxide, if you had 2 moles of iron oxide, you could look back and say, that must have come from 4 moles of iron. What am I getting at here? We are now in a case where for any chemical reaction, not just this one, any chemical reaction, if you know the quantity of just one chemical partaking in that reaction, just one, you can find out the amount of any of them, of all of them. And this is an incredibly powerful thing to be able to do. This process is referred to as stoichiometry. That's what it's all about. The idea that for any chemical reaction, if you know about the amount of one chemical that's involved, you know about all of them. Again, not nearly enough time to illustrate just how powerful this could be between you and I, but just a few examples. I mean, for one, breathe in. As you breathe in, the oxygen, your body is using that oxygen. It is using a fixed number of moles of oxygen, and from that it's producing a fixed number of moles of carbon dioxide, fixed number of moles of water, producing energy with that. But again, if you know the amount of just one of those substances that goes into that process, you can figure out how much of all of the others is present. So many different things we could use this for. Just a couple of examples here. Maybe some of you do some beer brewing at home. If you do, we can use stoichiometry to look at, well, if we know how much glucose we put into our mix and how much goes through the fermentation process, we can figure out how much ethanol, how much of our alcohol would come out of it. Similarly, we could wait till the end of the experiment and measure the alcohol content, and from that we can calculate back and figure out exactly how much glucose has gone through the fermentation process. Again, if you know about one substance, you know about all of them. Another example, maybe you're very greenhouse conscious and you want to know exactly what it is that we're doing to our world. Driving cars, combustion reaction that we've discussed. So we burn octane in the petrol tank, it reacts with oxygen, it produces carbon dioxide and water. If you know how much petrol you're putting into your car, you can calculate exactly how much carbon dioxide you're putting back out. Again, just know one of them and you will immediately know all of them. This is stoichiometry. So, if this is what we can do, let's actually stop and have a look at how we might go through this process. How do we go from knowing about just one chemical to knowing about any of the others? To do this, once again, we're going to use our example here. We're going to use our rusty car. So, here we have our familiar chemical reaction, our familiar car that's rusting away. Suppose we were in a situation where we knew the amount of iron metal that we had, this one here, and we wanted to know how much rust we were going to eventually end up with in this process. So This was the question. This is what we're trying to find out about. We can do this in 3 simple steps. In fact, I often refer to this affectionately as our 3-step plan. So, the first step in that plan is finding the number of moles of our known substance. Your known substance is the one that you know about. Maybe you know the mass that you have. Maybe you know the concentration and the volume. But one way or another, you know the amount. Specifically, you know the number of moles. And then you and I have been playing with tools, little equations like this for the last few topics so that we'd be ready when this has come. You've been doing that first step for topics for quite some time now. That first step, find the number of moles, your mass divided by your molar mass, or concentration times volume. I know you can do that. So now we know how many moles of one substance we have in that chemical reaction, that chemical equation. Now that you've got that, the second step is to find the number of moles of the unknown substance. What's the unknown substance in your chemical reaction? It can be anything you want, any other chemical in that reaction at all. And the way that we find that, the number of moles of that unknown, we take the moles of the known, our first answer, and we multiply it by what I call a molar ratio. It's a simple fraction that we get from our chemical equation. All we're doing is looking for the coefficients. The unknown goes on the top, the known goes on the bottom. So coefficients are just grabbed straight from the chemical equation and they give us this simple fraction. Let's have a look at how we might build this simple fraction right now. Back to my question here. I said that we knew about our iron and we were looking for our iron oxide, our rust. So if our molar ratio is meant to be our unknown divided by our known, I can simply look at the coefficients in the chemical equation. The coefficient, the number in front of my unknown, that's a 2. So 2 goes on top of my fraction, divided by the coefficient in front of my known, that's a 4. So 4 on the bottom. This is how we build that fraction, and that's really the only new skill we need to be able to do stoichiometry. So that is my molar ratio. That helps us find the number of moles of our unknown. The third and final step, well, let's illustrate this, I guess, in story fashion. If you go home and then say to your brother, sister, partner, mum and dad, I'd like 3 moles of water for a drink, please. They're going to look at you like you're mad. No one talks about moles in their day-to-day. They talk about masses, concentrations, volumes. So what is this third and final step? We know how many moles of this substance we have, but no one wants to know moles. They want to know something else. So convert it back into something more everyday. You might want to turn it back into a mass. Mass equals number of moles times your molar mass, just like we've been doing already. Maybe you want to go for a concentration or a volume. Again, anything from your tool belt will do. So this is stoichiometry. This is what we've been building towards. The idea that for any chemical reaction, any you can think of at all in your life, in the world, if you know the quantity of just one substance that's involved, you can find out about all of them. Come back for the next topic and we'll walk through a couple of examples together.